All right. Hello, everyone, and welcome to the session 11 of the second day of Western tracks of BTR 8 on electric vehicles and charging infrastructure. My name is Amirali Soltanpour, and I will be serving as the session chair. Before we begin, just a quick note, each presentation is allocated for a total of 20 minutes, around 15 minutes for the presentation and 5 minutes for Q&A. Please keep an eye on your time so we can stay on schedule. And please remain muted when not speaking and use the team chat to submit your questions. I will monitor the chat and facilitate the discussion following each presentation. So let's get started with our first presenter, Trisha Ramadoss. Trisha is a postdoctoral researcher at North Carolina State University. Her research focuses on electric vehicle adoption and the social and economic impacts of transportation investment and energy transitions. Trisha will present barriers to installing electric vehicle charger in multi-family housing. Trisha, please go ahead. Floor is yours.
Hello everyone. Thank you for joining today. Let me just share my screen. And let me know if there's any issues with my audio.
Your sounds great.
Does it look good?
Yep, have it in full screen.
Okay, great. Um, yeah, so thank you everyone for joining today. So today I'll be talking about barriers to installing EV charging in multifamily housing. And this is a project that I worked with my co-authors Scott Hardman and Alan Jen from UC Davis from towards the end of my dissertation. Uh, so hmm, just give me a second. I'm having some lag. Okay. So EVs continue to be popular even in California. So this is data from the first half of this year. So despite a drop in U.S. federal tax credit policy, EVs are still popular, continuing to spread. Um, so it's important as EVs diffuse to more of the population to think about how traditionally underrepresented groups will interact with and own EVs. So EV adopters are home charging. So charging your EV while you're at home is essential for those people for EV adopters. It's because it's often cheaper and more convenient. But people in apartments or people who live in multifamily housing or MFH often don't have home charging. About less than a quarter of U.S. multifamily housing residents can charge at home, from a study from G et al. And lack of home charging can often be inconvenient for multifamily housing residents who are looking to adopt EVs. At the same time, the breadth of barriers to installing EV charging in multifamily housing is still unclear. In the peer-reviewed literature, it's been mostly perspectives and meta-reviews with just a few qualitative studies. In order to understand this issue, why charging access is low in multifamily housing, qualitative studies and qualitative analysis um, can be useful for such new areas of study because surveys would likely miss important yet unknown topics is in such a new area of study. So this study that I'll be discussing uses qualitative analysis so that we can get into some in-depth exploration of the barriers to building EV charging in multifamily housing. And it's important to focus um, on apartments and multifamily housing residents because these households are more likely to belong to minority communities or to have lower incomes. And as we transition towards cleaner vehicles, it's important to make sure that our new transportation system doesn't just reproduce the inequalities of the past. So in this study, um, when I say qualitative analysis, we conducted some semi-structured interviews with different multifamily housing stakeholders, and we focused across California because uh, of the high EV adoption. which allows us to see problems that certain other areas don't encounter yet. So in this analysis, we conducted interviews with stakeholders. We recorded interviews, created transcriptions, and used post-interview memos or notes we wrote after interviews to kind of track the topics that we uncovered and to help guide interview recruitment. The analysis on the transcriptions was three-step axial coding, which I'll go into in a couple of slides, and that was based on grounded theory by Corbin and Strauss. So the people we interviewed came from three large groups. They came from apartments, which are multifamily housing that renters live in, condominiums, which are usually owner occupied, and what we call assistance programs, which I will discuss in a moment. So stakeholders from apartments came from two main groups. We had 11 property managers and 5 property owners. So property owners can be individuals or corporations, and these are people who own multifamily housing or apartment complexes or buildings. They often don't interface directly with tenants. Instead, they hire property managers who can go by a variety of names in order to handle the day-to-day operations of the building. And these PMs are usually the people who interface with tenants. We also interviewed stakeholders from condominiums. So condominiums or condos are often owner-occupied multifamily housing structures. And so we interviewed 8 residents and 1 general manager. And then the general manager plays a similar role to property managers in apartments. But in the third category of people we interviewed are stakeholders from assistance programs that are aimed at installing EV charging in multifamily housing. So there are 2 types of assistance program stakeholders we interviewed. The first are programs that provide financial assistance, so that's like rebates and money to stakeholders from apartments or condos who are looking to install EVs. And the second type are implementers, who are groups that actually do some project planning and project management to install these chargers. The interviews we conducted progressed as conversations between the interviewer and interviewee, and they were semi-structured in that they covered the following topics. So, for example, we learned about the interviewee's role and the characteristics of the multifamily housing, and we would ask questions like, how large is this apartment complex, and how many applicants do you have for this incentive? We covered topics about the EV chargers that they were considering, and the characteristics of these chargers, such as what charger speed did you install, and were you required to make any electrical upgrades. We asked about tenant and resident interest in EV charging, the motivations behind installing charging, and then we asked about their installation process and whether they encountered any issues, and then costs and management, whether the costs were as they expected or if they encountered anything unexpected. The analysis was 3-step axial coding. First, we conducted line-by-line coding, which we assigned codes, which are like themes or tags, to each sentence in the transcript. Then we conduct axial coding to identify common themes. And in this step of the coding process, we review and group and modify the initial codes, and try and merge any repeated codes and try to find commonalities between the initial codes. And then finally, through selective coding, we develop a framework to conceptualize and to really understand the barriers, and the barriers interviewees discuss to installing chargers. Okay. So through selective coding, we tested several classifications and decided that four classifications best separated the kind of issues interviewees bring up about installing chargers. So those four categories are technological, so that's issues related to physical or electrical or technical limitations of the building or of chargers. Finances, or economic issues, which are related to costs and finances. Institutional barriers, which are related to rules, procedures, and processes of organizations that these apartments and condos have to interface with. And then social psychological barriers, which are interpersonal relationships, beliefs, feelings, and perceptions and preferences. So overall, we identified 14 main barriers. Um, and so I can't get into depth. I won't go into depth for all of them, but as you can see, electrical upgrades and costs, which are pretty well identified in the literature and with stakeholders. Those were the most frequently mentioned issues. So electrical upgrades were issues relating to changing the electrical infrastructure to install chargers. So that could be like installing new wiring, new paneling, increase. So those are just modifications of the building, but there you could also modify the electrical service to a complex or a building. Which is an even larger electrical upgrade. So about 21 interviews mentioned issues related to electrical upgrades. And unsurprisingly, cost was another often mentioned issue. So these are any expenses that are incurred to install chargers. So that's the cost of chargers, but also ongoing maintenance fees, ongoing management fees, and other one-time or reoccurring costs. So 20 interviews mentioned some kind of costs as an issue. So I'll just highlight two other barriers and go into a bit more depth on those. Sorry, I'm having some issues. So I'll talk about electrical contractors and issues with incentives and implementers. So one barrier that we discovered interviews talking about was finding electrical contractors. So the process of finding contractors can be very difficult. So interviewees told us that contractors could be unwilling or inexperienced, and their estimates can vary wildly. And the breadth of issues interviewees experience is pretty large. So one interviewee told us that their project was too small for contractors. Another one told us their project was too big for contractors. And one said that contractors are not willing to do a small number of level 1 chargers, but another one said that they weren't willing to do so many, just they weren't willing to build so many chargers or work on such an old building. So estimates can be very different, and stakeholders often have to consult several contractors to come up with end up with a bid or to find the right contractor. So one interviewee told us of the 8 contractors that came to bid, I ended up with only 4 bids because some people just threw up their hands and said, you know what, this is really beyond us. Another category of issues people run into is working with incentive and implementer programs, because working with these programs can introduce friction. And this may be an issue that's more common in California or other regions that have a lot of incentive programs to increase EV adoption. So requirements from these programs can introduce some costs that are unexpected. Applications can be long or difficult to fill out, and implementers can introduce delays and that frustrate multifamily stakeholders. For example, one of our interviewees said, "There's very specific reasons why I'm so turned off by the whole program." Another one said about filling out forms, it did feel like, how do I fill out all these grant forms and how do I do all this stuff? It was a bit daunting. Oftentimes these implementers or incentive programs can be unresponsive to stakeholders, and that also can discourage them from this process. So, comparing this study, the barriers we identified to others in the literature, we identified a few that have yet to be discussed, including the difficulty of finding electrical contractors. But it's important to understand, applying our 4-category framework to these barriers, that the barriers are pretty complex. They're more than just issues of cost or technology. There's often layers of institutional or social barriers on top, on top of these issues. So to conclude this presentation, I would say that some of the barriers that we identified definitely need technical or market solutions. Like, the costs are high and there are difficult electrical challenges especially for these older buildings. But there are several barriers that either institutional or social, or social or psychological, that could be solved with policy. So policy that would simplify incentive programs or help train electricians, or referral programs, or increasing permitting staff could, in fact, help reduce a lot of the barriers to installing EV chargers in multifamily housing. So with that, I think I'll stop to take questions.
Thank you so much, Trisha, and thanks for ending right at the time. Checking chat box, I haven't seen any question. I can ask one. So we know that California, in like investing on public charging infrastructure, is one of the progressive state. Um, is do you feel like it's the same story with the multifamily charging infrastructure investment in the state? Is it like by far ahead of the other state, or there's some gaps still there compared to public charging infrastructure?
Um, I'll say that the public charging infrastructure in California is still, um, it's not reliable enough for multifamily housing residents. I don't think I have exact numbers comparing California to the rest of the country, but the chargers are often offline or broken, and I I think there's a figure that's like only maybe a quarter of apartment residents can walk to a public charger, um, can access a public charger from where they live. That might be across the whole country. I think it's probably the amount of EV charging in apartments is quite high in California because there's so much adoption. There's very high adoption in the state, and especially if you look at the Bay Area or the LA area, there will be a lot of apartment charging options. Um, I think there's still a lot of work to do because the adoption is still higher than the access available to them.
Perfect. Thank you.
Thank you.
Okay, so we can move on to our next presentation. Our next presenter is Iason Liagkas from the University of Michigan. Iason research focus on electric vehicle charging network, infrastructure planning, pricing strategy, and fleet electrification. Iason will be presenting 2 presentations today. The first one is behaviorally informed joint optimization of charger placement and dynamic spatio-temporal pricing for electric vehicle networks. Iason, please begin when you're ready.
Thank you, Amirali. Hello, everybody, and welcome to my presentation. Let me share my screen. Um, okay. All right. All right. Perfect. This presentation, can you hear me?
Iason, excuse me, just a heads up, we are seeing in your presenter view.
Um, is this better now?
It's not full screen, but it's not in the presenter view anymore.
Okay. All right. Let me start for the interest of time. And hello, everybody. Welcome to my presentation. The title of this presentation is Scalable Optimization of Electric Vehicle Charging Networks, Combining Column Generation with Reinforcement Learning-Driven Pricing. So in 2024, we had 17 million of electric vehicles sold worldwide, and 2025 we had 22 million of electric vehicles sold worldwide. And as you see here in this graph, the global electric vehicle sales from 2014 to 2024 has an exponential rate of increase. And also the infrastructure for electric vehicle charging stations, it's a big market with investments from the private and public sector. It is estimated that we're going to need in the future about 82 billions to support 50% of electric vehicle sales. And also here in the United States, there is an infrastructure gap because we have 28 electric vehicles per public charger. That is almost 3 times the recommended ratio of 10 to 1 by the European Commission. So the contributions of this presentation, of this paper, is that we have developed a computational framework for for placement decisions driven by user behavioral response and operator profitability. Then we are modeling the choices of the users. They can choose charging between different times and different locations, and the demand is sensitive of what is going on with the pricing and what is its charging station is offering. And also, this is a scalable computational framework that is inspired by column generation, and also we're combining reinforcement learning for the dynamic pricing of the electricity sold in those charging stations. So the problem statement is as follows. So suppose we have a city with Z zones as candidate parking locations to install chargers. Charging prices vary by time, space, and demand for charging. Competitors are present with fixed prices, and the charging demand function depends on time, space, and competitors' prices. So the utility function is comprised of the intended location and time that each user wants to charge, the selected location and time, which might not be the same, and then the operator. So we have utility value for each commuter and its charging station from the available ones for that commuter. And commuters, to calculate their utility, they take into consideration the total electricity cost that they will incur, and then the space relocation cost in case they end up charging in a different location than the initially intended one, and the same for time. We got earlier relocation cost and later time relocation cost. So how are users choosing between different nodes for charge? They have an initial intention of charging, say, node 11, but they also consider charging in adjacent nodes, provided they find better utility there. And the probability of charging in a specific candidate station is analogous to the utility they find on the station. Now, ideally, we would like to solve this computational problem, but it is not computationally tractable, and I will explain why, and I will offer solutions. But what we would like to solve is an optimization problem that in the utility function, in the objective function, it minimizes the net profits, which is total earnings minus total costs. And then we want to calculate the expected occupancy, impose chargers capacity, budget constraint, we have a specific budget that we cannot like create infinite amount of charging stations or invest infinite amount of money in charging stations. Then we need to define a minimum and a maximum price that we offer electricity in our charging stations. The prices also have to define prices of the competition. And we also have a threshold for users that if the utility falls below a specific threshold, then the user has the right to go for, the user will go for other means of transport. It could be bicycle, public transportation, or walking. And yeah, then we want to define the probability of choice for each user. And we also have an accessibility requirement. Say we want to put charging station in a specific area of the city or the map that we are examining. So the computational difficulties that we are facing now is that we have non-convex objective function because we're multiplying the price that we sell the electricity by the occupancy. And then as far as the calculation of probability of choice of charging stations by each user, we have variables in the denominator of this fraction. So we're going to transform this model into a column-based formulation. So a column is, as you see here, a vector that has zeros and ones, and ones stand for placement of charging stations. Say we want to place two chargers, one in node 10 and one in node 11. So the formulation is here, and it's comprised of two elements, the charger allocation element and the pricing element. So what we have is we want to find the optimal price at any given time step that will increase the immediate rewards and all the expected future rewards. And then from these prices, we can calculate the profits that we're putting in the objective function of the charger allocation model. So again, the charger allocation model now that is column-based, it has again the maximization of net profit. Then we have the constraint that a zone can be selected in at most one column. And then we have the accessibility constraint again that we had earlier, the budget constraint, and a binary column selection variable to choose between the optimal columns at the end. Yeah, here is the pricing problem that I explained. But again, we have some computational problems. All the combinatorial combinations of all the combinatorial complexity is very, very big for a big map. We have 2 to the power of the nodes that we have in our map. And then the profits that are created here are not known beforehand to be put as a parameter in the objective function of the optimal location selection, right? So for that reason, we have developed a computational framework that works as follows. We start with a random initial set of columns or candidate locations. We have a placement there, and then we evaluate those placements in a simulation environment using reinforcement learning to figure out the optimal pricing profits. And we're putting those evaluated columns in the reduced master problem. We solve the reduced master problem. We extract information that is named dual values, and then we use those dual values to generate new high promising for profitability candidate locations. And then we do this procedure again and again till we are no more able to produce promising profitable new locations. And when we have gathered all the optimal locations, available optimal promising locations, we solve the allocation problem. So let's go through the reduced master problem. Is the optimal allocation problem of charging stations that I showed earlier, but now the selection variable is not binary, but it's continuous in order for us to be able to collect dual values from the constraints. And with those dual values, we are applying some heuristics to generate new columns. Okay, so we got 4 heuristics. The first heuristic prioritizes nodes as candidate placements that have very high demand for charging. The second heuristic prioritizes nodes that produce high dual value constraints in the reduced master problem. The next heuristic prioritizes zones and nodes that have high demand for charging and also have participated in profitable columns, in the so far columns produced. And then finally, we got the final heuristic that is Monte Carlo, and it's an exploration heuristic that picks random nodes from the map, and we evaluate those nodes. When we have generated a new column or new candidate locations, we want to evaluate them, and what we want is we want to evaluate the reduced cost. So this is right here, but the reduced cost has the first term that it is the profits. So we don't know the profits, so we're using simulation and reinforcement learning to figure out what would be the profits, the maximized profits for this environment and candidate location. So in this reinforcement learning environment, we have different states that are defined by the occupancy of our stations, and also the previous price that we offered, the competitor's price, and the total reward at the end of the episode. We also have an action space that it is the prices that we choose to put in our charging station to sell electricity. And then we have a transition probability that we're learning from state to state, and that we're learning with reinforcement learning. And then we have the rewards function, which is immediate rewards for each time step, and then total rewards at the end of the episode. And the algorithm that we're utilizing here is the PPO algorithm from reinforcement learning, and this is the whole computational framework. And we have run some experiments. So the experiments we have 10 runs in a 4x4 grid network, and we draw statistical inference by all the results that we are observing. So this is the 4x4 map that we have here. On the upper green map, what you see with green color is that the green color is the demand for charging for its node. So what we see here, for example, node 11 has the highest demand for charging, and the demand is the same for all time steps. Okay, it doesn't change between time steps. So what you see on the lower left is the blue color is the nodes that were selected in those 10 runs as optimal placement for charging stations, and the arrows are how many. The width of the arrows is how many users deviated from their original intention and they chose a different node to charge. In the lower right map, what you see here, the yellow nodes give us the competitors' charging stations, and the heavier black circle around them symbolizes the amount of users that they have served. So what we wanted to test is what happens if we miscalculate the demand. So meaning that we expect a specific demand, but later the demand for charging is different. So in the first column, we have underestimation of the demand. In the middle column, we have that the demand is indeed what we expected. And in the third column is we overestimated the demand, meaning that the demand in the training data set is higher than the testing data set. So what happened is when we are overestimating the demand, we tend to raise prices. As you see here in the second row, red color means in two of our 4 stations, we have increased prices. That didn't happen in the previous examples, only so only for one time step and one slot here. And what you see on the third row is the amount of users that we served, right? And what we observed here that there is a statistically significant difference between the users that we serve that are less. We served less users when we overestimated the demand, and we have higher prices. Now we did again the same the same experiment, but now instead of changing the mean of the demand, we're changing the variance. And what we observe is as we increase variance, again, we tend to increase the price a little bit, but not that severely as when we change the mean of the demand. And the amount of users being served in different types of demand variance is very similar. What we were interested, though, is to figure out how this miscalculation of the demand affects our profitability. And what we infer is that in the case that when we are overestimating the demand, we serve less users, and this has a result of decreasing revenue. But in all other cases, we do not see any statistical significant difference in the revenues if we underestimate the demand or if we under or overestimate the variance in the demand. So what we want to avoid is overestimation of the demand. We want to avoid overestimating the demand. So and next we wanted to see what happens of how our computational framework takes advantage of the users being able to choose between different time steps for charging. So what we have here, we have a higher demand for charging in the third time step, a peak hour demand, and other demands are lower. Okay, and what happened is that in our charging stations we tend to increase the price offered for charging in the peak demand hour, and we observed an allocation of users that intended to charge the third time step. They chose to charge in the second, the first time step, and sometimes in the fourth time step. Users from the second time step moved into the first time step, and we also ran the experiment again. But users didn't have the ability to choose between different time steps, but they could only choose between different nodes. Okay, and what we observed is that the model was able to capture the profitability by the ability of users choosing between different time steps. And what we observe here is for those two cases, the difference in the revenue. Thank you. Do you have any questions?
Thank you, Iason. Any question for Iason? Okay, since we are on time, let's move on to your second presentation titled Integrated Fleet and Charging Infrastructure Co-Design under Vehicle Level Cyclic Stability.
All right.
Please continue when you're ready.
Yeah. All right. So the next presentation is titled Integrated Fleet and Charging Infrastructure Co-Design under Vehicle Level Cyclic Stability. So the statement of this problem, again, we're trying to figure out what is the optimal placement for charging stations for electric vehicles. But now we're working for a fleet operator who is minimizing his long-term infrastructure and operational costs. So in order to make this minimization, this operator has to make a first stage decisions of siting and sizing the private charging infrastructure, and the second stage decisions, which is energy feasible routing, charging decisions, demand assignment, the load demand assignment on his fleet, and then fleet composition, meaning composition of the ratio of electric vehicles in the fleet and gas vehicles in the fleet. What is the optimal ratio? And then fleet sizing. How large should the fleet be? The defining feature of this presentation is that we require vehicle level cyclic stability and terminal energy compatibility, meaning that a vehicle that starts from a particular origin goes to the destination to deliver the load, and then within the produced route, it comes back into the origin. And if we're talking about an electric vehicle, the electric vehicle has to come back to the origin with energy levels at least as what they were in the beginning. This feature allows us to have a routing schedule that can be run on replay without the need for overnight charging and overnight replacement relocation of vehicles. And we named this problem the stable fleet charging infrastructure planning problem. So the contributions of this presentation or this paper is that we have developed an integrated fleet and charging infrastructure co-design framework for mixed electric vehicles and gas vehicle operations under repeatable planning horizons. Okay, so the decisions for charging placement and vehicle operations are combined. This is what I mean here. And then we introduced the vehicle level cyclic stability and terminal energy compatibility with joint infrastructure routing planning. Then we saw that the cyclic stability fundamentally changes the structure of the operational routing problem. And we convert the problem from a simple mean cost flow to a terminal compatibility problem, which is increases the computational complexity. So for that reason, we developed a scalable decomposition-based solution framework for large-scale stable fleet and infrastructure planning. And then we demonstrate that the computational scalability of our computational framework on large time-expanded transportation networks. So let's take a look at the networks that we're operating on. It's time and energy expanded. So nodes, we have nodes that represent candidate physical stations, and we got dummy origin and dummy destination nodes. And then we have arcs like travel arcs, charging arcs, waiting arcs, and dummy arcs. So the major variables in our formulation are the placement variables, the sizing variables, and then we have like routing variables, vehicle routing variables, demand routing variables, or load routing variables. Then we have assignment variables, meaning assigning load to specific vehicle. And then we have unmet demand variables. Okay, and let's go through the problem formulation. It's arc-based. In the objective function, we want to minimize the total infrastructure investment cost for the fleet operator. We want to minimize the charging costs, the unmet demand costs, and then we got the moving vehicle costs and waiting vehicle costs that are incurred. So we have, as far as the constraints, we have charger placement constraint, charger capacity constraints, and then we have demand balance, meaning that the balance for each OD pair is going to be the demand for load. It's going to be partitioned between electric vehicles, gas vehicles, and unmet demand. Then we have demand flow conservation constraints, and then we have demand injection and absorption in our map. We also have vehicle capacity constraint, meaning each vehicle has a specific amount of capacity of passengers or load that it can transfer. And then we have routing feasibility constraints, meaning that each vehicle starts from the origin dummy depot and ends at the destination dummy depot. We have the vehicle flow conservation constraints. We have the gas vehicle terminal compatibility, okay, the cyclic stability. And then we have for electric vehicles, energy stability and terminal cyclic stability constraint. Now, we're calculating the total occupied miles traveled by electric vehicles and the total occupied miles traveled by gas vehicles. And we impose a minimum ratio of miles traveled by electric vehicles in case like there is such a directive from government or something like that. So the solution approach that we have proposed is breaking down the problem into a master problem and a sub-problem. In the master problem, we make the decisions regarding the placement and sizing of charging station, and the sub-problem, we make decisions regarding operations. The sub-problem makes all the decisions regarding routing, charging, fleet sizing, and fleet electrification ratio, and it's solved to optimality with column generation. And we also have an adaptive smart system that we choose which columns are allowed to be in the next Bender's iteration, columns for the sub-problem from previous Bender's iterations to the current running Bender's iteration. So let's go through the master problem. We're minimizing the infrastructure cost. We got the recourse cost variable. And then we have charger placement constraint. And we have the optimality cuts that are added as the algorithm runs. So let's go through the operational sub-problem, okay? We turned it into a column-based problem because the arc-based formulation, as we scale the problem, becomes very large, highly degenerate, and difficult to solve efficiently. While the tour-based formulation, the tours are the columns, embeds the energy feasibility and charging feasibility and cyclic stability within the produced columns. Okay? And the column generation avoids the explicit enumeration of all feasible tours. So what we change here to achieve this column based formulation is in the objective function now we have the total tours, cost, and unmet demand penalty. We have convex route selection constraints, reformulated charging capacity constraints, and path capacity constraints. And we have kept exactly the same. Anything that is out of the blue box here, the OD demand balance, the load flow conservation, and the electric vehicle utilization requirement. Now, we start by solving the reduced master problem. We start with a subset of routes for electric vehicles and ICE vehicles. And as we solve the reduced master problem, we extract again the dual values for ICE and electric vehicles regarding the vehicle capacity constraints, the convex route selection constraints, and for electric vehicles only, we extract the dual values pertaining to the charging capacity constraint of the reduced master problem. So then we move to this pricing sub-problem because we wanted to generate new promising routes or promising columns. So we want to find new columns that have negative reduced cost. And also those columns or routes have to abide by the already constraints that we have about path feasibility, energy, and tour stability for electric vehicles. And then we have the exact same pricing problem for gas vehicles, but we do not require the energy stability. And we have developed a specialized label setting algorithm over the time energy expanded network to solve this model faster. And when we reach optimality in the operational sub-problem, we extract dual values of the total sub-problem to generate Bender's cuts added to the master problem to repeat this process. Now, I want to underline a structural property, a major structural property of our computational framework, is that the routes that were produced from previous Bender's iterations with different charging placements are still feasible because the observation is that infrastructure decisions modify charging capacity limits of routes, not the underlying stable tour universe, meaning a previously produced route that required a charging station. Now we don't have the charging station. The route is still feasible, but the charging capacity is zero. So vehicles will not cross that, but will not choose this route. But this means that we can choose any of the previously produced columns from previous Bender's iterations. And what are we doing to choose them in a smart way? We're grouping those generated routes in similar groups called column signatures. So what is a column signature? Is any ordered sequence of visited physical stations with time and energy indices removed. Okay? Similar tours are grouped by using shared signatures. And then at the beginning of its new Bender's iteration, the bandit policy selects a high-scoring signature groups to initialize the reduced master problem. And how this scoring occurs is it's the frequency that a column was selected in the previous Bender's iterations. And also we have an exploration term that if a signature is not selected frequently, then we give some reward bonus points there for exploration purposes. So this is a computational framework. Now I'm going to proceed with some experiments that we did. First, we wanted to examine the computational impact of vehicle level stability. So what you see here, we had a 3x3 grid network, and we ran both formulations with stability constraints and without stability constraints on the arc-based formulation. And on the horizontal axis you see here is the percentage of activated OD pairs within our map. And in the vertical axis, we have the total solution time. And what we see here in those box plots is the running times with and without stability constraints. And the inference is that when we have stability constraints, the computational running time is significantly more, and it increases as we increase the percentage of activated OD pairs in our map. Then we have the comparison between our computational framework and the arc-based initial formulation. So again, we have a 3x3 grid network. In the horizontal axis, again, we have the percentage of activated OD pairs. In the vertical axis, we have the total solution time. And what we observe about the solution times with these box plots is that the arc-based, in the initial arc-based formulation, has a statistically significant higher solution time to get up to reach optimality compared to our computational framework that is always faster. And what we observe as the map becomes more loaded with OD pairs, then this time difference increases. And next, we wanted to examine three column picking policies. The first policy, what you see here, is no pull, meaning that on each Bender's iteration in our computational framework, we do not keep any previously generated routes, and we generate all routes for every iteration from 0, okay? And then the next policy is the full policy, meaning that we have kept all the generated columns, okay, from previous Bender's iterations. And then here is the bandit, choosing the policy that we do. And what we see here is that the solution time on a 3x3 network is with our bandit selection policy, we can achieve a significantly faster solution time. Then between those three policies, what we did is we broke down the solution time. And what you see here, the total solution time, and what you see here in the left figure is that the number of Bender's iterations and the number of column generation iterations per Bender's iteration. And what we observe is that the number of column generation iteration decreases among those three policies, with the lowest number of column generation iterations is when we use the bandit policy, while the number of Bender's iterations remains statistically similar between those three policies. And then what we examined is that we broke down the per iteration solution time between the master problem and the sub-problem components. And what we observe is that the master problem solves significantly faster. And also the total solution, the solution time of the sub-operational sub-problem decreases between those three strategies, with the faster strategy approach is when we choose columns with a bandit. Next, we applied the computational framework in a real map, so specifically the Lower Peninsula of Michigan, and we're using the data set for freight networks and freight loads named FAF4, and we have two maps: the optimal solution of electric vehicle flows in map A, and map B we have the gas vehicles. And this blue station right here is the optimal charging station placement. So what we can infer is that electric vehicle flows concentrate along charging supported corridors, like you see here, while gas vehicles serve more spatially dispersed regions throughout the map. We got gas vehicle flows everywhere in the map. And then we have that the charging infrastructure concentrates in high throughput regions, meaning this region over here. And lastly, we wanted to check what is the optimal electrification ratio of the fleet, and what is the sensitivity of it regarding the electricity cost and gasoline fuel cost. Okay, so the fleet electrification decisions are highly sensitive to both gasoline and electricity prices. Higher gasoline prices and lower electricity prices substantially increase the share of OD demand served by electric vehicles. In contrast, the optimal solution was insensitive to charging infrastructure investment costs because these costs are amortized over the lifespan of the charging equipment. Thank you. Are there any questions?
Thank you, Iason. There's one question in the chat. Someone Mitra asked, you have a variable on met demand. How did you get that data?
Okay, so the unmet demand is defined internally in the model, and this is this variable is minimized in order for us to place all the load in our fleet. But in case this is impossible to achieve, you can have unmet demand, meaning that you wanted to transfer some product from a specific origin to a specific destination, but you didn't have the fleet. So the data, the data set that we used for the experiment, and it's about real freight data transportation, is named FAF4. It's a well-known data set. But as far as the unmet demand is internal variable, it's not an external demand that we get from somewhere. Yeah.
Perfect. Thank you so much. Thanks for both presentation and sharing your work with
Thank you,
us.
Amirali.
Okay, moving to our next presenter, Bernardino D'Amico is a professor in School of Computing, Engineering, and the Built Environment at Edinburgh Napier University. His research focuses on computational methods, sustainability, climate policy, and more recently, causal machine learning for decarbonization and policy analysis. Bernardino will present beyond correlation using causal machine learning to estimate the impact of off-street parking on EV adoption. Bernardino, please go ahead. You're on mute.
Oh, perfect. Okay, thank you very much for the introduction. And okay, so yeah, so hello everyone. Thanks very much for the introduction. So as explained by the host, I will be presenting some recent research we've been doing here in Napier with Professor Achille Fonzone on the so-called charging divide. So we essentially looked at whether the higher adoption of EVs amongst a certain strata of household, namely those with access to off-street parking, such as a driveway or private garages, is a true infrastructure constraint, or is simply a reflection of some underlying socioeconomic privilege, or a bit of both. Namely, the aim of the research was to quantify the extent to which having a private driveway, so namely being able to charge the EV from home, is an actual, the extent to which this causes probability increase in owning an EV. So, of course, the transition to electric mobility is a cornerstone of many nations' commitment to net zero. and climate change mitigation. However, as the market has expanded beyond early adopters, when you look at the data, there is a stark divide seems to have emerged. Namely, households who own an EV seems to be much more likely to also have access to some sort of private off-street parking. If you look, for instance, at some recent data from England, by the Electric Vehicle Association England, they report that there is a probability, a 90% probability for an household that has access to off-street parking, given that they own an EV, and this is much bigger than random chance. So, of course, from a theoretical point of view, we know that off-street parking allows for cheaper home charging. So, as a consequence, those without it may face some significant financial barrier in deciding to buy an EV. But I guess the critical question for policymakers is this lower adoption caused by a lack of private parking, or is just a strong statistical association, a non-causal association, or partially causal, so to speak? So the reason we may have a strong statistical association between two or more variables, despite the absence of any direct causal effect, it has to do with the presence, of course, of confounding variables. So let's have a quick look at this toy example where we are dealing with three variables. We know that the financial capacity of a household causally affects both the ability to own an EV, because EV tends to, there is no second-hand market, so buying an EV tends to be more expensive than buying a combustion engine. But it also causally affects the ability to buy and own a house that comes with a private driveway, for instance, detached houses or semi-detached houses, as opposed to apartment blocks. Which, of course, this also in turn will affect the ability to charge the EV from home. So the problem is, of course, if we gather observational data, survey data, and we just look at the conditional probability of owning an EV, given that the dwelling as a private parking, we can risk overestimating the direct causal effect of parking provision on EV ownership. Because you are unable to disentangle the direct causal effect of X on Y from that of Z on Y, as well as the indirect effect of Z on Y mediated by X. We can see this graphically in this toy example. So, of course, to move beyond correlation and being able to estimate causal effect, we can essentially do two things. We can either run a randomized control trial, and clearly this is often not possible. It's either impractical or simply impossible, like in our case. Or we can use some causal inference method applied to observational data. So in this case, we are using a so-called causal Bayesian network. Like standard Bayesian networks, these are graphical models where, of course, each variable is associated with a conditional probability distribution given its parents. The difference with a vanilla Bayesian network is that in a causal network, arrows represent direct causes between variables. So all this local conditional distribution, they factorize into a full joint distribution. So we can essentially compress all the full joint into a product, a factor of local conditional probabilities, essentially, over all the observed variables. And this is the full direct acyclic graph that encodes our causal Bayesian network. I will skip how we got to this, but very briefly, this can be either specified based on expert knowledge, as it used to be done back in the 90s, for instance, or they can be partially learned directly from data. So when, of course, we can then, once we define this, once we build this causal Bayesian network, we can then express the causal effect of interest, in this particular case, the effect of parking provision on EV ownership, so variables V7 on Y, as a post-intervention probability distribution of Y, given that V7 was intervened upon and was forced to take on a certain value off-street parking, true or false, so to speak. In this case, the treatment is a binary variable. And this differs, indeed, from conditioning. So as Yuda Pearl, a computer scientist, one of the fathers of modern causal inference, puts it, I think it's worth paraphrasing his writing. He explains very well that when we intervene on a variable in a model, we fix its value, we change the system, and the values of other variables often change as a result, not necessarily. When we condition on a variable, we control on a variable, we really change nothing. We just narrow the focus, our focus to a subset of cases in which the variable takes the value we are interested in. So what changes then is just our perception, or I should say the perception of the model about the world, not the world itself. So essentially, I think it's important to clarify that what we are trying to estimate here is, what we are trying to predict is not an observation, but is the effect of an intervention, of a hypothetical intervention. Because, as I said, we cannot run a randomized control trial in this case. So the question is, okay, how do we compute this post-intervention distribution, namely P of Y given do V7? And if we have all the relevant variables to model the data generating process we are interested in are included in the data set, so we observe them, we have data for them, we can simply mutilate the causal graph. In other words, we remove all the natural incoming edges into the treatment variables, and we set it to our chosen value. And by doing so, we can isolate the causal mechanism of interest. And this yields to a truncated factorization of the full joint. So this will provide an unbiased prediction of the interventional effect. The problem with this, however, is that it only works if indeed we can measure all these relevant variables. But in real applications, this is almost never the case, because we have unmeasured, so-called unmeasured confounders. Suppose, for instance, we have a variable U1. We know that there exists such a variable, and this variable causally affects both Y and V1, both the outcome and the treatment, or some other variable V1. But we have no data for it. We obviously cannot compute the local conditional probability of Y given its parent U1, because we simply have no data. So in such cases, this causal framework hinges on the concept of identifiability, meaning whether the causal effect of interest can be still determined from the available observational data. And this may be the case or may not be the case. So when identifiability is not guaranteed, in other words, when we are dealing with some latent variables in the model, we can apply this framework called do calculus. Specifically, we applied a derived criterion from this do calculus, so-called the backdoor criterion. And do calculus is essentially just a set of three deterministic rules that, under certain independency conditions, the one on the right side of the three equations, these rules allow us to rewrite post-intervention probability distributions in terms of observational distributions. And these three rules allow us to exchange actions for observations, remove observations, or remove interventions. The statistical independency conditions, of course, the one on the right side of the three equations, they can be checked using a purely graphical algorithms, such as the so-called D-separation, because effectively the graph is encoding these independency conditions. One important note is that this do calculus is proved to be complete. By the way, the inventor of this do calculus is again this Alan Turing Award computer scientist Yuda Pearl. It's not something I invented myself, just to be clear. The calculus has been proved to be complete, which essentially means that if the causal effect of interest is identifiable, there is a guarantee that there exists a finite sequence of applying those three rules to derive the causal effect of interest just from observational data. So going back to our original question, quantifying the causal effect of having access to off-street parking on EV ownership, to answer this question, first of all, we use the built causal Bayesian network that I've described previously to estimate those post-intervention distributions, given an external intervention on parking provision, variable V7. And then, in a manner very similar to an RCT, a randomized control trial, we can calculate the treatment effect. So if we're dealing with continuous variables for the outcome variable, we can actually calculate the average treatment effect. In this particular case, the outcome variable is actually a discrete categorical. So the way we worked the delta TE, we just calculated this effect as a contrast in the probability distribution of the outcome Y. And here is the post-intervention distribution required to answer our query. So you can see on the right side, we only have observational distributions. In other words, the effect of interest was proved to be identifiable using this backdoor criterion. And you can see that all we need is essentially controlling for a sufficient adjustment set, namely variable V8 and V9, were found to be sufficient for identification of the causal effect of V7 on Y. There is a full proof in the conference paper of this. So looking at data, probably should guess, from this distribution, then, as I said, we can work out the treatment effect. And these are the numerical results. So we find that essentially providing off-street parking as a proxy for home charging, essentially, triggers a reallocation of probability mass towards more advanced EV adoptions. Probably one thing I should have said is that EV, as I said, the outcome variable has 4 states. First one is the household already own an EV. Second value is they are thinking to buy one soon, they are thinking to buy one later, or they are entirely disinterested. So as we can see from the results, as I said, an intervention enabling a hypothetical intervention, enabling a household to charge their house from home, essentially would yield a 2.3% lift in percentage point for the first category, I already own an EV, and a plus 2.7% point lift in immediate intent to buy an EV. Now, this seems very small, but actually probability lift, but actually they represent roughly 70% in relative increase in EV ownership probability compared to the baseline ownership probability, which at the time of collecting the data was roughly 3.3% in Scotland. So a hypothetical intervention providing off-street parking to the entire population, to the entire sample of the population of Scotland would increase EV ownership from 3.3% to more than 5%, so to speak. Crucially, the probability mass is largely drawn from a minus 5.5 percentage point contraction in the third categories. So all those households that are thinking to buy an EV in the future, which suggests that parking provision acts as a catalyst. It accelerates existing latent intent into adoption rather than generating interest from households that are largely disengaged, that are not considering to buy an EV. For this category, as you can see, the causal effect shows a very negligible shift in probability, only 0.5 percentage point. on an average baseline of 50% of respondents who said that they are not interested to buy an EV at all. And then, of course, we wanted to check how far off this effect estimate would be if we were to rely on observational distributions instead of employing a causal framework. And so we also computed this delta observational. Essentially, it's just a contrast between the conditional probability of EV ownership given that we observe parking provision instead of intervening upon it. And as we can see from the bar chart on the right, there is a minus 2.2 percentage point reduction in non-participation, which again, it's highlighting a confounding bias from the raw observational metrics. If we were to rely on the observational association alone, we would mislead policymakers because we would overestimate the impact of home charging or infrastructure on the most disengaged household, essentially, the one who are not interested to buy an EV, whether or not they have access to off-street parking. We also did a further analysis. We also used our causal Bayesian net to estimate the causal effect of household income. Again, these are hypothetical interventions, of course, on EV adoption. And so we worked the contrast between the two post-intervention distribution of Y given a hypothetical intervention on variable V1, which is the income. So for the specific case, we binarized essentially the variable income in two values, low and high, respectively representing household with an income either below or above the sample median value. And as we can see, the causal effect of forcing, so to speak, household income from low to high, it shows a massive contraction in the fourth categories, meaning that high income does convert this disengaged household into future intent to buy EV, unlike the presence or absence of off-street parking. So to conclude, these results seem to suggest some sort of structural hierarchy with income or financial availability serving as a market entry prerequisite. So it clears the affordability necessary to move household into the EV adoption pipeline, whereas parking provision only serves as a conversion catalyst. It moves household from latent intent into realized imminent EV ownership. So our analysis essentially indicates that for those households, roughly 50% of Scottish households that are not considering or not interested to buy an EV, any policy intervention to facilitate home charging is unlikely to trigger adoption until the more fundamental barriers of vehicle affordability is eventually addressed, either through, reducing EV prices. Thank you for your attention. I'm happy to answer any question.
Thank you so much, Bernardino, for your presentation. I'm checking chat box. There's no question yet, but feel free to continue the conversation there.
Amirali, can I ask a question? Since I'm a co-host, I can unmute myself. Is that okay?
Yeah, sure. Please go ahead.
First of all, thank you for this presentation. I really appreciate. My question is, you are looking at the off-street parking, and definitely, did you control for the income, of course? Because my thinking is, parking is not like government will provide the parking. You have the house or something, and you have the off-street parking and other things. So I'm just wondering, if you take the income effect, how it looks like between low income and high income. And because in general, my thinking is if someone is higher income, they're more likely to buy EV. That's maybe the current research is showing. And for the policy interventions, government perspective, how your research actually going towards some policy directions? Thank you.
Yes. Yes, thank you very much for your question. These are two very interesting questions. So regarding the first one, Essentially, I did not control for household income, and the reason why I did not control for household income is because assuming, of course, that these adopted causal graph is a faithful representation of, the real system out there, where, household income, for instance, has a causal effect on EV ownership, but also has a causal effect on dwelling type and a bunch of other things like tenancy type, owning outright, etc. Then if this is a faithful representation of the reality, then this causal inference machinery that I described, do calculus, essentially tells us that you don't need to control for household income. All you need to do is controlling for these two variables, V8 and V9. So these are the only two variables that are needed to control in order to avoid any spurious association, statistical association flowing from the variable V7 through the backdoor all the way to variable Y. And there are dozens of these kind of paths. But so by controlling for these variables, in theory, if of course, if we believe in this framework, then yes, you don't need to control for. So the idea is essentially that these frameworks allows you. It provides a mathematical way to decide what to control or what not to control for. Insofar, we believe this graph is a faithful representation of the real data generating process. The second question was about, sorry if I can ask what was this?
Second question was like policy related, like since.
Yes.
Excuse me, can I interrupt?
Sure.
We're
Your time, yeah.
short on time. Yeah, please continue your discussion
Can
in the
I?
chat so
Okay, thank you.
other participants can also get
Thank
your
you.
response. Thank you so much. Excuse me.
No
So
worries.
we're moving to our next presenter, Sajjad Vosoughinia, graduate research assistant at Michigan State University. His research focused on EV charging infrastructure planning, operations research, and large-scale optimization methods. Sajjad will present multi-objective planning of electric vehicle charging infrastructure for tourism along Wisconsin's shoreline. Sajjad, whenever you're ready.
Thank you, Amirali, for the introduction. Let me just share my screen. Can you see in the presentation mode?
Yes.
Okay, thank you. Hello, everyone. My name is Sajjad, and the title of the study that I'm going to present today is multi-objective planning of electric vehicle charging infrastructure for tourism along Wisconsin shoreline. So, as you may know, electric vehicles reduce traffic-related air pollution by eliminating on-road emissions. And EV adoption is increasing nowadays because of factors like fuel prices, upfront costs, and demographic trends. But also, there are some key barriers to adoption, like range anxiety, long charging time, and inadequate charging infrastructure. By the end of 2025, Wisconsin had 0.7% EV market share. California led the nation with 4.8% EV market share, and the US average was almost 1.9% EV market share. Tourism travel patterns typically involve longer distances, extended dwell times, and concentrated flows along scenic corridors, which require coordinated planning. So an effective strategy integrates level 2 chargers at destination with DC fast chargers along the corridor for en route charging. So the main questions that we address in this study is what is the optimal combination of slow and fast chargers? What is the most effective investment balance between slow and fast chargers? And how do budget limitations, EV market share, and technology advancement like battery capacity influence charging infrastructure planning? So this study focuses on the Lake Michigan Circuit area in Wisconsin, which is defined as the area within 10 miles from the lake's shoreline. So generally speaking, long-term stay locations such as hotels, motels, these are good locations for installing level 2 chargers because these are locations that people stay there for like more than 5 or 6 hours, and level 2 chargers takes longer to charge a battery. It takes like 4 hours or 5 hours to charge. And also short-term stay locations such as retail, restaurants, gas stations. So these are good locations for installing DC fast chargers because these are locations that people stay there for like 1 hour or at most 2 hours. And DC fast chargers takes like 10 minutes or 15 minutes to charge a battery. So in the left-hand side figure, you can see the level 2 candidate locations that we have in the area. So these are all the destination locations or any hotels, motels that we have in the area. And the right-hand side figure shows the DCFC candidate locations that we define. And this is this is after aggregation and after mapping the short-term SL locations to the access point that we have along the main corridor in the area. So in this study, we have two main objective functions. So the first one is minimizing unserved energy demand at level 2 chargers. That would be because of lack of level 2 chargers or maybe because of their full occupancy. And this unserved energy demand is redirected to the closest DCFC station and they charge there. And the second objective function is minimizing average user inconvenience time at DC fast chargers, including detour time, charging time, and also queuing time. And we have four main decision variables, which is X and Z for level 2 chargers and X and Z for DC fast chargers. So X is a binary variable indicating if we are building a charging station at that location or not. And Z is an integer variable, shows how many chargers we are building at that location. And we have two main constraints. So the first one is budget constraint. We ensure that the total cost of building chargers, the level 2 chargers and DC fast chargers, is lower than the budget that we have. And the infrastructure cost includes three main components for both level 2 and DC fast chargers. So the first one is the cost of charging a station. So this cost is for site preparation, the land cost, pavement cost, and any labor cost that we need at that location. The second component is the charger cost, which is the cost of each individual charger or equipment. And the third one is the electric grid upgrade cost, which is the cost of actually upgrading the grid to be able to provide the required power at that location. And the second constraint is a feasibility constraint that ensures all EV trips along the corridor are feasible. And we ensure that by tracking the state of charge of users traveling along the corridor, and we have a threshold, and if their state of charge goes below that threshold, so actually we call that trip and its demand as an infeasible demand and infeasible trip in that solution. So regarding the solution approach, multi-objective problems can be solved using two main approaches. So the first one is transforming the problem into a single objective formulation using weighted coefficients or epsilon constraint method. And the next one is solving it directly using multi-objective evolutionary algorithm. So in this study, we use NSGA2 algorithm, which is an evolutionary algorithm for multi-objective problems. So before getting to the detail of the algorithm, so we have to know what domination is. So for example, if we have two different solutions, solution A and solution B, we can say solution A dominates solution B if both of them are feasible and A is no worse than B in all objective function and also is strictly better in at least one objective function. Or solution A is feasible while solution B is infeasible. Or if both of them are infeasible, solution A dominates solution B if it has a lower constraint violation. So with that, we go to the detail of the algorithm. So the first step is initial population. The algorithm starts by generating an initial population of chromosomes with each chromosome representing a potential solution. And each chromosome is encoded as a combination of binary variables, shows the station location, which is X for level 2 and X for DC fast chargers. And also, integer variable shows the number of level 2 or DC fast chargers at each location. So in the figure below, you can see an example of chromosome. So once we have XNZ for level 2 and XNZ for DC fast chargers, so we know the location and number of chargers. So now we have to evaluate each solution to calculate all the objective functions that we have, all the state variables, and any constraint violation that we have for each solution. So for level 2 evaluation, the first step is trip generation. So we calculate the total number of attracted trips at each destination location, as we defined in the previous slides, using the IT trip generation manual. So IT trip generation manual provides a guidance on calculating the total number of attracted trips based on the number of employees at each hotels and motels. So once we calculate the total number of attracted trips at each location, so we have to distribute these trips to different origins we have in the state. Using travel distance between each origin and destination, and also using the statewide OD demand. And in the next step, so we made some assumptions for user charging behavior. And using this assumption, so we calculate the final state of charge for users when they get to their destination, and also how much energy demand they need at destination to charge their battery. So based on that, we have the total EV demand and total energy demand at each destination location. And using the location and number of level 2 chargers, we can calculate the unserved EVs and unserved energy demand at each destination location. And these are the demand and EVs that make detour to the closest DCFC location to charge there. And for DCFC evaluation, so using the location and number of DCFCs, we do the traffic assignment along the corridor, and we assign different EVs and different trips that we have to the available charging station along the corridor. And with that, at each charging station location along the corridor, we know the EV demand and energy demand, and we can calculate the detour time, queuing time, and charging time at each DCFC station. So based on this evaluation, for each solution, we have the objective functions, we have the state variables, and all constraint violation, and we can compare different solutions with each other. So then we have the main process or the main loop of the NSGA here. So it starts by an initial population of chromosomes. And first it goes for evaluation, as I discussed, to calculate all objective function and constraint violation. And then we have to do the non-dominated sorting and crowding distance comparison. So the left-hand side figure shows the non-dominated sorting. Actually, we do a pairwise comparison between all solutions that we have, and those solutions that are not dominated by any other solutions, they form the first non-dominated set or the first rank or I1 in the figure. And then we remove these solutions. And for the remaining solutions, again, those solutions that are not dominated by any existing solutions, so they form the second non-dominated set or I2 or rank 2. And we do this process until we put all solutions in different non-dominated sets. So as you can see in the figure, I1, I2, and IN. So these are the non-dominated sets that we have in this population. And once we have the non-dominated sets, so we have to do the crowding distance comparison inside each non-dominated set. So the right-hand side figure shows the calculation of crowding distance comparison. For example, for solution I, crowding distance is calculated by the summation of normalized X and normalized Y. And actually, crowding distance shows how close is each solution to its neighbors. And the higher crowding distance means better because if it has a higher crowding distance, it means that that solution is located in an area that we don't have so many solutions. So actually, this is better for us because we are searching the area better. So once we calculate the crowding distance for all solutions, so we sort the solutions inside each non-dominated set. In the next step, we do the tournament selection, crossover, and mutation to produce the offspring from the parent solutions. And then in the next step, we do the evaluation for the offspring solution to calculate their objective function and their constraint violations. And after that, we combine all the parent solutions and offspring solutions and do the non-dominated sorting and crowding distance comparison for all the solutions that we have now. And after that, we just keep the first n solutions and they would be the parents for the next generation. And we do this process for a certain amount of, a certain number of iterations. So for the numerical example, here we have the base scenario assumptions and parameters. So we assume the infrastructure budget limit is 20 million. We assume the EV market share is 25%. And for the battery capacity, we assume 70 kilowatt hour. So these are the main parameters that we have in this study and in the next couple of slides. So I'm going to present the sensitivity analysis that we have done for these parameters. And also we have in-vehicle value of time for users and waiting value of time for users, which is, for example, $25 per hour or $36 per hour. And these two value of time, so these two parameters are calculated based on the US DOT guidance on travel time value of time. And then we have the result of the proposed solution approach or the proposed NSGA for the base scenario that we defined. So in the figure, you can see the optimal Pareto frontier that we obtain for the by the NSGA. So the x-axis shows the average delay at DC fast chargers, which is the second objective function. And the y-axis shows the unsafe energy demand at level 2 chargers, which is our first objective function. And in the table below, we are comparing the result of our proposed NSGA with the result of another algorithm, which is simulated annealing or SA here. So to be able to solve it with SA, we combine the two objective functions that we have using weighted coefficients, and then we solve the problem using SA because SA is able to solve a single objective problem, so it's not able to solve multi-objective problem. And here we selected three different solutions from the Pareto frontier, which is the first solution in the Pareto, the middle solution, and the last solution of the Pareto to compare it with the SA result. So if we compare the unsafe energy demand at level 2 chargers, we can see that the result of SA is much higher than the result of three selected solutions from NSGA. And if we compare the DCFC delay, we can see that the middle and the last solution of NSGA has a higher delay compared to the SA. But again, the first solution of the NSGA has a lower value compared to the SA. So it means that if we compare just the first solution and the SA result, we can see the first solution of NSGA has a lower value for both objective function, and we can say that this solution is dominating the result of SA, or generally we can say that the obtained Pareto frontier dominates the SA result and it is converging better than the SA algorithm. And also if we compare the total delay time in the network, again, we can see the first solutions that we got from NSGA has a lower delay time compared to the result of SA. And here we have the optimal locations for level 2 charging stations in the left-hand side figure, and also the optimal locations for DC fast charging in the right-hand side figure. Then we did the sensitivity analysis for infrastructure budget. So we defined three scenarios, 7 million, 20 million, and 23 million. And as you can see, increasing the budget from 7 million to 20 million. So it has almost 16.6 megawatt hour reduction in unserved energy demand at level 2 chargers, 7.6 minutes reduction in DCFC delay, and $24.1 thousand per day increase in user benefit. So this user benefit is calculated based on the value of time that I explained earlier. And by increasing the budget from 20 to 23 million, we have 4.3 megawatt hour reduction in unserved energy demand. We have 6.3 minutes reduction in DCFC delay and $12.2 thousand per day in increase in user benefit. And in the figure, you can see the optimal Pareto frontier that we got for each scenario. And then we did EV market share analysis. So planning only for a 25% EV market share, while the current EV share in the state is only 1%. So it can lead to inefficient investment because of underutilization or future shortage. So because of that, here we defined 3 different scenarios for EV market share, which is 5%, 15%, and 25%. And if we compare the results, we can see that by increasing the EV market share, the number of DC fast chargers and also the DCFC infrastructure cost doesn't change too much. And it is the same for 5% and 15%, and it just adds 2 more chargers for 25%. But level 2 chargers is increasing proportionally with the EV market share. And that's because level 2 chargers takes longer. It takes like 4 or 5 hours to charge a battery. But DC fast chargers takes like 10 minutes. And because of that, DC fast chargers can serve so many users during the day. And so by increasing the EV market share, we don't need to necessarily increase the number of DC fast chargers along the corridor. And finally, we did the battery capacity analysis. We defined 4 different scenarios for battery, which is 50, 70, 100, and 150 kilowatt hour. And by comparing the results, we can see that by increasing the battery capacity, the DCFC infrastructure cost is reducing while the level 2 infrastructure cost is increasing. And we have the same pattern for number of DC fast chargers and also number of level 2 chargers. And also, if we compare the DCFC energy demand along the corridor, so we can see that it is reducing significantly. And that's because by increasing the battery capacity, there are so many trips along the corridor that they can get to their destination without any en route charging because they have higher battery capacity. So they don't need en route charging during their route anymore. And also, if we compare the queuing time at DCFC, we can see that the queuing time is decreasing because we have lower demand, and also DCFC refueling time is increasing because we have larger battery capacities. And also, if we compare the total delay time in the network, we can see by increasing the battery capacity, the delay time is reducing significantly. And as a conclusion for this study, so this study formulates a problem as a multi-objective optimization solved using NSGA2 algorithm, which generates a Pareto frontier and provides decision makers with a range of trade-off solutions. And under the base scenario, almost 5.5 megawatt hour, which is 2% of total level 2 demand, is unserved and is redirected to the closest DCFCA stations. And approximately 2.2 to 2.4 million is allocated to DC fast chargers to ensure trip feasibility. And we saw that increasing the budget reduces the user delays and unserved demand, and also early DCFC investment remain effective, but level 2 infrastructure scales with EV adoption. And also we saw that larger battery capacities reduce network delays and shift investment priorities toward level 2 charging infrastructure in the network. And that's it. Thank you for your time, and happy to answer
Thank
your
you so
questions.
much, Sajjad. We don't have time for live Q&A, but please keep the discussion in the chat box with Sajjad. And our final presenter today is Behdad Ghafarnezhad, PhD student and graduate research assistant at Michigan State University. His research focuses on transportation electrification and network modeling. Behdad will present a roadmap for fleet electrification and public EV charging at Michigan State University. Behdad, please go ahead.
Sorry, now, do you have my voice? I was not able to
Yes,
unmute. Okay, thank you.
can hear you.
Amirali, and also, do you have my screen?
It's not full screen, but we
Yeah, I
can
will.
show you.
Uh,
Yeah, awesome. Thank you.
Okay, thank you. Hello, everyone. Thank you for attending to my presentation. As Amirali said, the title of my presentation is A Roadmap for Fleet Electrification and Public EV Charging at Michigan State University. Here you can see an outline for my presentation. First, I'm going to explain a short introduction. Transportation sector has a high negative impact on environmental by producing greenhouse gas emission and consumption of petroleum. Therefore, alternative fuel vehicles could be a good solution to reduce these impacts. Among these vehicles, electric vehicles nowadays is one of the most popular option. In this slide, you can see a summary of different EV charging infrastructure types and their attributes. In terms of this topic, EVs and EV charging literature, campus and institutional settings are underrepresented despite growing EV adoption among students, staff, and fleet vehicles. Now I'm going to explain MSU public chargers current configuration and MSU currently has 6 level 2 EV charging infrastructure having 16 ports and 1 DCFC charger with 2 ports. We have the charging station data for level 2 chargers since 2014 when the first one I think was installed there, and we have the DCFC data from August 10th, 2023, exactly the same time that these chargers started to work. And in the next few slides, I'm going to explain some statistical analysis on the charging session data that we had. In this slide, we, as you can see in the blue box on the left below, we divided the whole day into 5 time intervals. And as you can see on the graph and figure on the right, we have higher energy demand for level 2 chargers during early morning and midday hours, while the peak energy demand for DCFC happens during afternoon and evening. This slide has the daily distribution of energy dispensed per day for 2 charger types by days of the week also. A significant less energy demand happened during the weekends. The difference is significant for level 2 chargers during weekends. And also the weekend energy demand for DCFC is slightly higher in comparison to weekdays. But however, level 2 chargers demands have a significant difference between weekdays and weekends, but the DCFC demand, as you can see, remains relatively constant. Here is the monthly pattern of the energy per day for different months of the year. During the summer months, such as May, June, and July, we have less energy demand for level 2 chargers. And the highest demand happened during October and November for level 2 chargers. We have also a decrease in demand during December and January, which will be probably because of the holidays that we have in those months, and students and faculty also leave the campus probably. And also, as you can see, there is no specific monthly pattern for DCFC demands, since maybe these stations can be used for other, like for intercity trips and other types of trips that are not only located for local users. Here you can see a heat map for hours of the day, like the heat map of usage of the stations, of chargers. This is for showing the number of stations per active days for each charger. As you can see, we have higher number of stations in some of the stations located in the middle and east side of the campus during the midday hours and morning hours. And another trend that we can see was a considerable late night demand for one of the stations on the east side of the campus. Here is the yearly trend of the energy consumption in the chargers, public chargers, I mean. So as you can see, there is a significant increase in charging demand during recent years. However, there is a small decrease during 2020, which is probably because the pandemic situation that happened in that year. Now I'm going to talk about the future public charging at MSU, which includes the optimization frameworks that we use to find the optimized configuration for the future charging at MSU. So at the beginning stage, we use the dynamic traffic simulation, DynaSmart, to generate trip trajectories and travel time and distance schemes for the networks. Also, for trajectories, for EV trajectories, we calculated the initial and desired SOC of the trips. We considered the home charging availability in the simulation, and two types of trips are generated for EVs. One are feasible, another is infeasible. The feasible trips are those that can happen and can be done without en-route charging. I mean, they can reach their destination without en-route charging based on the state of charge and the energy en route will be used. But infeasible trips that are those trips that needs en-route charging for completing the trip. We use the feasible trips for level 2 charging analysis and infeasible trips for DCFC charging optimization. I mean. So here is a summary of the DCFC framework. We use the SA algorithm to find the optimal location of charging station and use the golden section method to find the optimum number of chargers in the location that were found. Here is the geographical result of the DCFC. We have done it for three EV market penetration rates, 1%, which is almost the same as current market of EV in the Lansing area and Michigan, and 10% for near future maybe, and 20% for further future. You can see the results and allocation of the chargers in these three scenarios. For the level 2 charging campus, for level 2 optimization for charging campus, again, as I mentioned, we use DynaSmart and simulation to generate trips at the beginning stage. Then we calculate the energy demands using the trip, work destination trips and feasible trips also to minimize the infrastructure cost and user costs and find the optimum location and number of chargers. We had some assumptions for this framework, for level 2 framework. We considered work destination EV trips for potential charging demand, and we assume that EV will charge if their state of charge go below 60% at the work destination. And for their charging pattern, we assume that vehicles are charged to 60% SOC if this means gaining at least 50%. Otherwise, they will charge just enough to gain 50% of increase in their state of charge. Three scenarios we consider for calculating level 2 charging demand: charging at the destination zone if the charger is available at the destination zone. Otherwise, charging at the closest zone that have charger will happen, involving a walking detour. Since it's a small campus area, we assume that walking detour for short distances is possible for a user. And the third scenario is not charging, which demand remains unserved, and we assumed a penalty in the objective function for this part. So there are some analyses that could somehow support these assumptions. You can see the DCFC initial and SOS and the state of charge analysis. Unfortunately, we don't have the initial and end state of charge for level 2 charging in the data. However, we have level 2 charging session duration analysis and level 2 energy dispense analysis. As you can see in the table, most of the DCFC charging begins when SOC is below 50%, and most of the level 2 charging session take less than 4 hours and less than 30 kilowatt energy dispense. Here's the objective function. It has three terms. The first one is infrastructure cost, the second is users detour cost, and the third one is the unserved energy demand in the network. Here are some constraints. The first one is for calculating different scenarios, which the sum of them should be equal to total energy demand arrive at destination zone J, and also other constraints that you can say. I skip this for sake of time. These are the results, as you can see, geographical results and also base values that we assigned for our parameters that we used. Here are some other results. So For the lowest market penetration rate, as you can see, infrastructure is concentrated in a single high demand zone. In this scenario, well, the model just have the walking detour for other zones. But as demand grows, coverage expands, leading to reducing walking detours and improving service proximity, which means the model prefer installing more chargers locations and reducing walking detours when the demand increased. The unserved energy demand is low in stay low in almost all scenarios based on the value that we considered for the penalty of unserved demand. And also, as you can see, the share of detour energy decreases in the model in higher market penetration rates since the number of stations increase is the result of these scenarios. And now I'm going to talk about MSU fleet chargers and operation shortly. So we have 4 depots for only MSU fleets, and it's not available for public charging. It has 44 chargers, level 2 chargers having 7 kilowatt power. And also we have the data for 36 EVs and 191 non-EVs or conventional EVs. All of them has the tracking system Samsara for gathering the data of them. In this graph, as you can see, for each depot, the average daily energy dispense is very low in compared to their capacity. For example, in the first one, the IPF loading dock, we have 10 chargers, which could have 7 kilowatt per hour, but the total during a day is less than 80 kilowatt hours. So all of them are very underutilized based on the data that we have. Also, we calculated, we found the locations, most of the locations that fleets stayed for more than 30 minutes around Michigan all over, since these fleets are used for further trips, not only in-campus trips. So this location could be a good candidate for future charging installation outside the MSU campus if they decide to replace their non-AV vehicles with EVs, since all of the further trips happens with non-EVs currently, and EVs only used based on the data that we have for in-campus trips. On the right side, also, you can see the total energy, average energy dispense during each day of the week in the all of the depots, charging depots. I'm going to explain the future fleet electrification. So in this blue table on the left side, we have annual vehicle mileage and energy consumption of MSU fleet. As you can see, the total mileage for non-EV is more than 5.7 times of the EVs. I should mention that this data is for half of which was the available data, is for half of the 2024 and the whole 2025. So per vehicle mileage for non-EV is 8.5% more than EVs if we divide this mileage by the number of vehicles that we have data. This is what we can see. And also the efficiency of non-EVs had more than 6% decrease in 2025, which could be because of the increased engine idle time, while EV's efficiency has a subtle increase. Also on the right side, you can see the energy cost and cost per mile. The fuel cost per mile for non-EVs is about 7 times that of EVs, as you can see, and the fuel cost per mile in non-EVs has a 6.5% increase in 2025, while the fuel price for EV has a 2.7% decrease. Here you can see the some analysis in terms of cost savings, current and existing EV usage. As you can see in the blue table above, they have saved more than $62,000 in less than 2 years in terms of fuel costs. And if we assume that we will replace the current non-EVs with EVs, assuming the same EV efficiency and the same travel patterns for non-EV, based on the prices that we have, the data of the prices of the fuels that we have, if we replace our non-EV vehicles with EVs, we could save $357,000 more than this during this 1.5 years in terms of fuel costs. And also for maintenance costs, we have done the same analysis, assuming the US Department of Energy reports that EV maintenance costs average 6.1 cents per mile, and for the gas powered vehicles, 10.1 cents per mile. This is what current EV fleets save during the same time interval as I mentioned, almost $6,000 in less than 2 years for the maintenance costs. And if we replace the non-EVs with EVs, we could save $34,000 during the same time interval.
Sorry
Here-
to interrupt, Behdad. If you
Okay.
please wrap up in
Okay,
a
this
minute.
is just 2 slides remains. So at the left side, you can see the distribution of fleet daily energy consumed for EVs, and at the right side, you can see the fleet daily distance traveled by non-EVs. So if we assume the current EV chargers that we have, 44 level 2, and the same EV efficiency, which is 1.79 miles per kilowatt hour for current EV fleets, and if we assume we have 9 hours of day available for the chargers, in the worst case scenario, if all the non-EV vehicles distance they travel is 3,000 miles, which is the 99% of the current distribution, existing chargers could support more than 200 EVs to replace the non-EVs currently. So they are very underutilized, as I mentioned. So for conclusion, public EV charging demand, as you saw, is increasing with noticeable seasonal and site-specific variation. Level 2 charging demand peaks during midday hours, while DCFC demand peaks in the afternoon. Central campus, northwest and southeast zones are better suited for level 2 charging based on the optimization result, which is consistent with the observed demand patterns. And the northern campus boundaries require greater investment in the DCFC charging infrastructure. And electrifying the remaining fleet is expected to lead to a significant fuel and maintenance cost saving, and existing fleet infrastructure has a capacity to support more than 280 electric vehicles in the future.
Thank you so much, Behdad. We have
Yeah.
no more time. Thank you,
Thank you.
and thank all the presenters, and thank all the audience for their contribution. Without further ado, I just adjourn the meeting and hope you enjoy rest of the conference. Thank you so much.
Thank you.